of Synopsys on the title, Synopsys OptoCompiler, Electronic-Photonic co-design of photonic integrated circuits. Jigesh Patel is a product manager of Synopsys Photonic Solutions Group. Jigesh has 20+ years of experience in fiber optics and communication systems. He received his master's degree in engineering from the Indian Institute of Technology. Prior to Synopsys, he has worked at National Institute of Standards and Technology and RSoft. Jigesh is a senior member of the IEEE. The floor is yours, Jigesh.
Thank you, Kaisuke. Thank you for inviting me, and thanks to the previous authors for very nice talks. So today I'm going to talk about a product from Synopsys. This is the Photonic IC design platform. The name of the product is OptoCompiler. And it is industry's first unified electronics and photonics design platform that combines mature and dedicated photonic technology with Synopsys' let's say, electronic design tools and methods together that enables engineers to produce and verify the complete PIC design quickly and accurately. So here is the outline. I'll begin with, let's say, with a quick overview of the photonic toolset within Synopsys Photonic Solutions, and the introduction to the Photonic IC design platform of the compiler that I mentioned. The next two bullets or the next two items are not exactly, let's say, the demo cases, but basically I will show how, let's say, you can carry out electro-optic co-design as well as Monte Carlo and corner analysis within the OptoCompiler PIC design flow. And towards the end, we will summarize what we saw. So this is something in the previous talk, James already kind of gave an idea that photonics and photonic integrated circuit technologies have penetrated many areas of applications. So some of the major, let's say, main segments are optical data communication, sensing, biophotonics, and say datacom related PICs. They find deployment mainly in the data centers, cloud computing, storage type of applications, and with the emerging push of, let's say, co-packaged optics or CPO, more and more deployment and high volume deployment are expected. In addition to, let's say, the data-centric infrastructure, the datacom type of PICs or photonic integrated circuits also find, let's say, deployment in cellular networks, military and aerospace applications. And also there are, let's say, emerging areas like in photonic computing, automotive, and consumer electronics, where, you know, this kind of deployment is increasing. The sensing is a diverse and big market segment, depending on the application. Sometimes also comes with the, let's say, regulatory requirements. VCSEL-based integrated sensors, for example, are used for face detections and, let's say, 3D sensing applications. And this kind of PICs find applications in consumer as well as R&D, aerospace and defense type of applications. So let's say LiDARs are also quickly, rapidly expanding technology and widely deployed in many areas, but automotive being the main ones. Biophotonics is another category that basically includes the consumer wearables and lab on the chip type integrated sensors. And then end product volume for this kind of PICs is also on the rise. So now let's look at the key challenges in photonic integrated circuit design and manufacture. To design PICs efficiently, you need dedicated design tools. The reason is that the photonics is not like, let's say, CMOS electronics. So here we deal with photons that travel in non-Manhattan shape waveguides rather than electrons that typically flow in Manhattan-type conductors. So the key point is that for photonics, it also was clear from the previous two talks, the geometry matters a lot. So that's why we say that photonics has RF-like behavior. Also, photons don't like corners, so they need to be guided around through, let's say, smooth bends in order to minimize the loss. So I showed an example here of a, let's say, a photonic integrated chip, where you can see that there is AWGs on the transmit and receive side, and you see the special shapes here, and those shapes are needed in order to maintain physical characteristics of the optical signal, that is the phase, amplitude, polarization, etc. You cannot, let's say, implement in a Manhattan shape, and then this kind of a peak won't work for this particular application. So the problem, because of this, let's say, curve shape, has a special, implication for the verification, because it can potentially generate a high level of false errors for design rule checks. And those violations are the result of snapping errors that occur, let's say, because of the conversion of these curves into polygons over a rectangular grid. So, so those are the type of, let's say, the issues that so far has kept the photonic integrated circuit design in the realms or the domains of the experts. And the electrical models and simulators, since are, that also has promoted the use of kind of, let's say, fragmented flows and in-house tools that don't talk to each other, and ultimately result in, let's say, low productivity and human error. For the foundry, the process of, let's say, the photonics is still the PDK, the quality of PDK, the maturity level of the PDK is still not at the same level as, let's say, the electronic PDK. And the curvy data impacts the optical proximity correction and the mask prep stages. So ultimately that results in, let's say, low performance and lower yield. So on this slide, there are three groups of, let's say, the photonic tools that are part of, let's say, Synopsys Photonic Solutions. On the left side, you see the photonic device design tools. Depending on the device, you have, let's say, different algorithms available to choose for beam propagation method, finite domain time difference, rigorous cover wave analysis, finite element method, and so on. Then in the middle is photonic circuit and system simulator, that is OpSim. And on the right is the photonic integrated circuit design solution. And that includes few products, and we shall see a little bit more details about OpSim and about, let's say, the Photonic IC design platform in the next few slides. So this is the block that basically shows different parts of electronic photonic design platform. So how the unified electronic photonic flow works. That is basically all these four blocks are kind of look like they are independent processes, but they work very closely together within the same design environment smoothly. So basically, as a user, it's a schematic-driven design flow. So you start with the schematic entry to the OptoCompiler, which acts as a design cockpit, and it has a complete custom and analog mixed signal capability. So the tool is aware of photonic nature of the layout and the synthesis. And it has exclusive photonic specific features that you generally don't find, let's say, electronic chip design tools. That is the seamless abutment for photonic auto align, assisted waveguide routing, and so on. Also, together, let's say within this OptoCompiler, you have also the verification stage possible through a tool called IC Validator. So once you have, let's say, the schematic, you would want to do the simulation. So for the simulation, depending on what type of photonic circuit you have, or whether it has how many electronic components it has, you choose the circuit simulators. So circuit simulators are dedicated depending on the domain of the integrated circuit. So let's say OpSim is a simulator, the default simulator for photonic integrated circuit. If you have electronic components, you want to, let's say, co-simulate electronics, photonics together in the same chip, you could also choose HSpice and FineSim, which are now known as PrimeSim Continuum family of tools. The third block that you see here is the Photonic Device Compiler. And the Photonic Device Compiler basically helps you create custom photonic devices. So even though, you know, the foundry PDKs are maturing, there is still a lot of customization going on or needed, let's say, on the photonic side. And so this this Photonic Device Compiler has a feature to do EO co-simulation with center of TK. Ultimately, you get a self, per device, you get a full cell with all the required views that are necessary for a schematic-driven layout flow. So this is how, let's say, a schematic-driven layout type design flow works. So you start from the left, so you have some concept. You capture that concept in form of a schematic. So you break down the concept into, let's say, individual constituent components. You prepare the schematic. You can prepare schematic using, let's say, the compact models that are pre-supplied with the library, or depending on the foundry you are using, you prepare the schematic using PDK elements or process design kit elements from the foundry. Then you can, of course, do the simulation if you want, but generally, once the schematic is done, you go to the layout stage. In the layout, also, you can do manually based on the PDK component that you are using in the circuit schematic, or in OptoCompiler, it's an automated way. So you can just, depending on the schematic connectivity intent, it automatically generates a layout. And then, of course, you, depending on your packaging constraints and your, let's say, available space on the wafer, you may want to make change to your layout. And so any change that you do in the layout will also have effect on the modeling side. So you could go back annotate those changing, run the simulation again, and, you know, if everything is all right, then move on to the next stage. So once the layout is done, then there are the verification stages that includes layout versus schematic check and design rule check. And ultimately, when everything is satisfactory, you go to the tape out. So starting from concept to tape out, everything means except this part, all these design stages are fully integrated within OptoCompiler platform. So although there are different tools, like, say, for example, simulation is a different simulator, schematic entry is done at one place, layout versus schematic, and DRC checks are done by another software. But everything from the user perspective, the entry point is one's design environment, and the exit is just the mask for the tape out. So as a user, you are not required to choose different software and everything. Everything is now automatically taken care of. So here is a view or a screenshot from OptoCompiler design environment. So just by looking at the design environment, those who are familiar with electronic IC design, for them, they will immediately feel at home that it looks very familiar, similar type of, let's say, the GUI. You have the schematic, through compact components, which could be PDK components or the library components. You have within your schematic electrical pins, photonic pins, photonic wire or the waveguide routes, electrical wire. And so all those components and the connectivity. So when you are, let's say, preparing the schematic, some of the basic connection checks are done right there. So you don't have to wait until, you know, the DRC errors gets generated in large number. So this kind of acts, you know, the design environment keeps some basic checks on how the connectivity is done, if there are any open terminals, if, and so on. So once your, let's say, the schematic entry is done, the layout, as I mentioned earlier, could be manual. You could manually either place all those components that you use in schematic, or you can have the tool auto-generate the layout based on the connectivity that you have specified in the schematic. So the connectors in the schematic, what happens that you specify connection between the two components, and the layout will automatically generate the correct shape to provide that connectivity. There are features like seamless abutment that make sure that even if, you know, the abutment is automatic and seamless, so that you don't run into a number of design rule check errors during your verification stage. All these layout functionalities have native support for curvilinear shapes. And so it's, let's say, photonics oriented. So anytime you make changes to the layout, it will translate into change in the schematic. So for example, you added a waveguide, you changed the shape of the waveguide, or any routing, anything you altered, that means those effects need to be taken into account during the simulation. And so the way you take the way you reflect the change in the layout back to the schematic is called back annotation. So whenever you move anything, you will see the corresponding components highlighted, showing you that, okay, these components or these PDK elements got changed, and you need to take the changes back to the schematic and run the simulation again to make sure that whatever layout related changes were done did not in a fundamental way alter your design. So all those options are there to back annotate the change from layout to the schematic. Once, let's say, your layout and schematic are ready, you create typically a test bench. So during the test bench creation, you have this OptoCompiler has the simulation and analysis environment where you basically choose the simulator for the circuit. So in this particular screenshot, the components are the photonic components. There are some components which are electrical as well as logical components. They are all components from OpSim, which is a photonic circuit simulator from Synopsys. And so if all the elements that you used are from OpSim, you will choose OpSim as your circuit simulator. The design environment will let you choose that. There are places where you specify your simulation related parameters, the probe points, and if there are electrical components or if the circuit is entirely using electrical PDKs, you have option to choose electrical circuit simulator as well. And if, let's say, I think I have one more slide that shows a mixed type of a design where there are electronic photonic components together. So in that case, for photonic circuit simulator is OpSim, and electrical circuit simulator depends on where the models come from, whether they are from PrimeSim HSpice or PrimeSim SPICE, which are electrical circuit simulators from Synopsys. The photonic device compiler block that you saw in one of the earlier diagrams where I was showing OptoCompiler, its function is basically to design, simulate, and optimize active and passive components. And as I mentioned earlier, depending on your design or depending on your device, you choose the appropriate algorithm. If you also need the electronic effect to take into account, you can have co-simulation with the ticket. And ultimately, the photonic device compiler gives a custom component. So the diagram on the right, we probably don't have too much time to go into very much details on it, but essentially, you start with the device geometry. This is an automatic process, also, although the steps or individual stages are broken down. A device geometry is the only place where user intervention is required to draw the, let's say, the design schematic. And then basically the simulation is done, the component is generated, all the views that are necessary in a schematic-driven layout are automatically generated. The self-sufficient cell is generated for your component design that you can, that can be based on a specific foundry technology, or it can be your own IP, but can be used, let's say, for simulation purposes, for layout purposes, for design rule check, and so on. So even though foundry PDKs are maturing, there are still many applications that would require some sort of customization for photonics. So this is where the photonic device compiler comes very handy. Now, with regards to the electro-optic co-design, the need for electronic-photonic co-simulation is not new. It has been around for even in older days when there were, photonic transceivers. People were using electronic circuits as electronic design tools. And when they needed to model only few photonic components, the way they used to do electronic-photonic co-simulation was to model photonic devices as electronics. Now, of course, since the photonic simulators are as mature as electrical simulators, there is not exactly need to do that. So this particular electronic-photonic co-simulation that I'm describing here is mainly to do with using domain-specific native circuit simulation. Use electrical circuit simulator for the electrical part, use photonic circuit simulator for the photonic part of the same circuit. So with regards to, let's say, the philosophy of electronic-photonic co-simulation within OptoCompiler, the idea is to provide an intuitive and seamless schematic creation experience to the designer. So designer doesn't need to be aware of demarcation of the boundaries between photonics and electronics. Just goes ahead with, let's say, the standard way of creating schematic. You have components from photonic circuit simulators. You have components from your analog lib or electrical libs. You again have some photonic components from foundries or anything. So in this case, there is no burden on the designers to make sure that there are domain conversion elements are there into your circuit or nothing like that. You just go ahead naturally creating your design. The simulator will take care of what it needs to take care of. So in those cases, when you do create a test bench, so here is a screenshot that shows various settings for a test bed. So for the simulator, you have choices available. So as a main simulator, since it's a mixed photonics and electronics, will be OpSim. You will specify the design variables. For the electro-optical co-simulation, you choose to enable it in this specific case because there are photonics as well as electronic components. And depending on which circuit simulator those models are implemented in, you choose the appropriate circuit simulator there. You can probe electrical ports, optical probes, everything together in the same environment. And once the simulation is over, you see electrical signals, optical signals, everything in the same, let's say, waveform viewer. There is no conversion of field to power or those kind of things. So native signals, not only the signals flow naturally into the native domain by circuit simulators, but also the waveforms are displayed in their respective native domains. Another is Monte Carlo and corner analysis, which is, a very common need for photonic integrated circuits in many areas as well, but we are talking about photonic integrated circuits. So OptoCompiler has powerful capabilities for letting a user do various kinds of process and mismatch type of analysis, set up Monte Carlo, set up corner analysis, depending on your, let's say, the interest. So one example is a simple one where you have Alexander interferometer using the photonic component, then you specify, let's say these components have typically the process variation and the parameter variation information comes from the foundries, but user can also, let's say, specify if the model was created by the user or the model was just an analytical model, you could also specify statistics. So in this case, the waveguide and the attenuator has some statistics specified. You set up the simulation as I was describing before. You set up the corners. There is a dialog window for corner that lets you tell the corner parameters, Monte Carlo related settings, and you just prop the output. This is the test bench you set up in OptoCompiler platform. And once the simulation is done, you view all the required waveforms. So like say, these are the waveforms for different variation in the parameters. You can have histogram, you can have eye diagram analysis. You can also have, let's say, you could also specify pass and fail criteria for your design. Say, for example, if power falls below a certain level, or if, let's say, the insertion loss goes beyond certain level, consider it's a fail. Those kind of pass-fail analysis you could also do. And if you had 100 runs, you can see how many runs the design passed, how many runs the design failed, and so on. So it's very convenient way of doing statistical analysis in OptoCompiler as well. The previous design had all the photonic component, but same is applicable for a mixed electro-optic co-simulation case as well. So you could have electrical components from analog lab or electrical PICs. You can have photonic components from photonic foundries. You can mix together. You can have statistics in electronics. You can have statistics in photonics. You can say combine effect the same way. So when you are setting up your Monte Carlo, you basically do the same way. Don't change your way of designing because there are now electronics and photonics together. Specify the statistics. You get the waveforms depending on what type of design it is. So I think I'm slightly exceeding my time. So just to wrap up, we saw various features and capabilities of a unified electronic photonic design platform from Synopsys. The platform is called OptoCompiler. It provides a unified workflow. It has integrated design rule check and layout versus schematic, supports electro-optic co-simulation, and comes with all the functionalities, including photonic ticket, photonic layout, photonic synthesis. So thank you for your time, and apologies, I went a little bit over the stipulated time, but open to the questions.
Thank you very much for your very interesting talk. Now, if you have any questions, please write in the panel, Q&A panel. I have a question. I think the electrical part, you can include capacitance and those kind of things. But let's say if you change the layout or wiring or routing, with it, can you also change the electrical characteristics of the simulation?
Yeah, so that's a very good question. So it's basically about backend notation. So the backend notation of photonic route is possible. So your question is, do you have the similar backend notation capability for electronic routes there? So currently we have limited capability in that regard. Some manual intervention is required. But Synopsys has a tool for electronic layout dedicated that is called STAR-RC. And so we are basically going to provide that functionality in a similar integrated way like it is for simulation and other things.
Thank you very much.
You're welcome.
Is there any more questions to Jigesh?
And along those lines, the 3D packaging related things also we are working on. So, because ultimately the what you described, the same electronic and thermal and other things would come in from the packaging impact too. So that's something we are working on.
Thank you. There's a question from Matthew. Does the platform have a script interface?
Yes. So generally it's a schematic driven layout. So the flow typically is you start with the schematic, everything is GUI driven, but the screenshots did not show was that lower part, every time you draw something, corresponding script appears below. So you could do the opposite way too. So you can start with the script and you will see that thing reflected in the schematic or in the layout, depending on where, for what you're writing script.
Okay, thank you very much. Any more questions to Jigesh? Okay, if not, then we have also Ristu and James on the line. So if you have any more questions to previous speakers also, please ask this moment. Okay, so this. So, yeah, I guess to summarize, I guess the trend is really, really everything becomes more and more complicated, meaning that starting from the multi-physics at the device level, and then you incorporate into the circuit level simulations, and eventually it will be more like a core simulation. So everything is moving towards that integrated solutions eventually, I think.
Yeah, I think so.
Thank you. Another question is from Jeffrey. Do any of these packages run natively on Linux systems?
So, sorry, James, go ahead.
Sure.
Okay.
I'll say yes. We run both on Windows and Linux for all the products.
Yeah. So OptoCompiler runs only on Linux, but individual components like the circuit simulator that is OpSim, you could run on Linux or you could run on Windows. Similar where the device compiler you can run on Linux or you can run on Windows. But the OptoCompiler platform runs only on Linux.
Yeah, we are also running on all platforms, and we have also something called application. For example, you can convert your models to an app. You can even any mobile device, and you can do, for example, some parametric study or optimization just by using the previously prepared application.
Thank you very much. But along the same line, does any of your simulators run on Mac?
Oh, yes.
Okay.
Yeah, we did in the past, but not as in the transition with ANSYS, we don't natively support Mac anymore.
Okay.
We don't have native support through virtual machine type of configuration.
Okay. Thanks. The question is from Matthew. Can you say anything about non-gradient optimization?
Yeah, I think I think that might have been directed at me from the two questions I see. Yeah, with respect to the adjoint optimization, that's a great question, because the method I'm talking, the adjoint optimization gives you all of those derivatives of the figure of merit with respect to parameters. So you're naturally talking about a gradient-based optimization, and you definitely run into the problem of being stuck in local minima. And so there are a variety of different strategies we've looked at to get out of that. Some of them are like thermal annealing type of approaches that are built on top of that. And another really interesting one is some work with the National Research Council in Canada, where they were using machine learning methods and principal component analysis to try and sort of restrict to a subspace, like an optimal subspace, where you could find a number of good starting points for the designs, so that you kind of get out of that problem of getting stuck in the local nearest minimum.
Thank you very much. Very interesting. Any more answer? Okay. Do you have any more questions from the audience? Okay, if not, then we are a little bit late at night. So I'd like to conclude this webinar. And I'd like to thank everybody, all the speakers. Thank you very much.
Thank you. Good night.
Thank you.
Thank you.
Thank you.
Have a good night, everybody.
Good night.
Bye-bye.